welcome back. Today we're going to talk about mass moment of inertia. Mass moment of inertia is always defined about an axis. That axis can be anywhere. So imagine a body. Okay, we're going to rotate this body about this axis, and these are our point masses. Just I have mentioned M1, M2, M3, and M5, M4. So, in order to find out the mass moment of inertia of this body, in this random shape, we need to add. This K1 means the distance about this rotational axis to this point mass. So, if this body consists of infinitesimally small mass, you have to keep adding all this like this, like m1 multiplied by the distance squared, and m1 k1 square plus m2 k2 square, and up to mn kn square. So this is practically difficult. So what we do for ease is that we assume that the center of mass or center of gravity of this body to be at a single point, and the distance between that and the axis of rotation is named as radius of gyration. It's called k. So if you put I equals mass, the entire mass concentrated at a single point at the center of gravity, multiplied by the square of radius of gyration, you will get exactly the same value of the added all this moment of inertia of all these small masses. So this is the fundamental equation that we use. I equals mass multiplied by the square of radius of gyration. So now there is one more thing called parallel axis theorem. There are many theorems, and this one comes in handy all the time. Suppose if we know the mass moment of inertia of a body which consists of different point masses about the center, the axis that passes through the center of gravity. So this is the center of gravity, and this is the axis that passes through the center of gravity. So you can say that if you take a body like this is the center of gravity, right? We're rotating about this. So in that case, we already know the value of the mass moment of inertia about the center of gravity. Then at any axis at a particular distance, say h, from that center of gravity, the axis that passes through the center of gravity, you can find the mass moment of inertia about any axis by the mass moment of inertia at center of gravity plus mh square. M is the mass of this point mass, the entire mass we consider as a single mass, and that multiplied by the distance between these axes, the axis that passes through the center of gravity and the new axis that we want to find the mass moment of inertia. So this is parallel axis theorem. Now what I need to make you guys understand is the physical significance of this. So when we get the mass moment of inertia, the angular momentum, mostly denoted in all the books by L, it's given by I into omega. So mass moment of inertia, once you get the mass moment of inertia multiplied by the angular velocity, see you should always consider the axis when you find this mass moment of inertia. If you are rotating a body about this axis, then to get the angular momentum, you need to multiply this mass moment of inertia by the angular velocity at which it is being rotated. This angular velocity will be same for all the point masses around. So it's given by angular momentum is I omega. Now torque is given by rate of change of angular momentum. So torque is given by d by dt of I omega, which because I is constant, it will be I d omega by dt, which means I alpha, where alpha is the angular acceleration, omega is the angular velocity. So we get the equation for torque. Torque is I alpha. It means that, say, if I try to, suppose if this body was being is in rotation like this, okay, now say this is a car wheel, okay, this is being rotated at this angular velocity like this. Now, okay, now it's being rotated at this speed. I need to increase its angular velocity. For that, I need to apply some angular acceleration, right? So it's being rotated at this speed. Now I need to rotate it faster. So I need to apply an angular acceleration alpha. But the torque which I can apply is limited. Say my vehicle's engine provides this much amount of torque. So the larger this part, the larger is the rotating body. If your torque is limited, if this I becomes big, what happens is your alpha has to be small. It means with your limited torque, if you want to give acceleration to change your angular velocity to a higher level, because your I is big for a bigger mass, your angular acceleration will be small. It will take a lot of time to accelerate. The same way, if your I is less, which means this disc or this rotating body is small, or its mass moment of inertia is small, you can accelerate faster. That is the meaning of this. That is the main use for this mass moment of inertia in this, how it is related to torque. Okay, thank you.